Regular languages. Finite automata provide a semantical approach to formal language theory with implicit algorithmic consequences. There is another well-known syntactical approach to finite state languages. It has been extensively studied due to its importance in practical applications such as the grep family of commands in Unix, and surely because of the beauty of the resulting theory. We refer, of course, to the class of regular languages. The reader should recall that a regular language is one that has a representation via a finite string of symbols taken from the members of a sigma together with union, concatenation, which we represent by juxt juxtaposition for regular expressions and strings, star, which means clean star, and empty set. Formally, we have the following definitions. Definition 6.13. Regular expression. A regular expression over sigma is an expression in the alphabet sigma union left parenthesis, right parenthesis, and empty set defined by induction on logical complexity as follows. One empty set and each member of a sigma is a regular expression. Two, if alpha and beta are regular expressions, so are alpha beta and alpha union beta. Three, if alpha is a regular expression, so is alpha star. Four, nothing else. Naturally, we drop the brackets where the meaning is clear. Definition 6.14. Regular language. We associate a language L of R, alpha, with a regular expression alpha as follows. 1. If alpha equals to the empty set, then L of alpha equals to the empty set. 2. If alpha equals to A with the A in sigma, then L of alpha equals to the set of A. 3. If alpha equals to gamma beta, then L of alpha equals to L of gamma followed by L of beta, which is by definition equals to the set of x, y such that x is in L of gamma and y is in L of beta. 4. If alpha equals to gamma union beta, then L of alpha equals to L of gamma union L of beta. 5. If alpha equals to beta star, then L of alpha equals to the star of L of beta, which by definition is the set of all strings obtainable from L of beta. We call a language L regular if L equals to L of alpha for some regular expression alpha. Example 6.15. Let L equals to the set of 0, 1, L of 0 followed by 0 union 1 star equals to L of 0 followed by L of the star of 0 union 1. This is by rule 3, which is equal to the set 0 followed by the star of L of 0 union 1 by rule 2 and 5, which is equal to the set 0 followed by the star of L of 0 union L of 1 by the rule 4, and which is equal to the set of 0 followed by star of the set of 0 union the set of 1, which is by rule 2, which is equal to the set of 0 followed by star of either 0 or 1, which is equal to the set x in 0, 1 star such that x starts with a 0. The relationship with the work of the previous sections is described by the following classical theorem. Theorem 6.16. This is from Klein. For a language L, L is finite state if and only if L is regular. Furthermore, from a regular expression of length m, one can construct a deterministic finite automaton with big O of 2 to the n states accepting L. Proof: we show how to construct the automata to accept regular languages. Clearly, empty set and the A in sigma are fine. Otherwise, a regular language is built from one of a lower logical complexity via one of parts 3 to 5 of definition 6.14. But now the result follows by the closure properties of theorem 6.12. The complexity of big O to the n comes from looking at the complexity of the inductive definitions of the machines for union, star, and concatenation. Conversely, suppose that L is finite state. Let L equals to L of M, with M equals to the tuple K sigma delta SF, a deterministic finite automaton. We need a regular language R, with R equals to L of M. Let K equals to the set Q1, Q2, Q3 until Qn, and S equals to the set of Q1 for ij in the set among 1 to 3 until n, and 1 is less than equals to k, which is less than equals to n plus 1. Let R of ijk denote the set of all strings in sigma star derivable in M from state Qi to state Qj without using any state Qm for M which is greater than equals to k. That is, we let R of ijk equals to the set of rho such that the tuple Qi rho yields in one step star to Qj lambda intersect for all gamma of the following, that Qi rho yields in one step to Qm gamma implies that the union of M less than K union the set alpha gamma equals to lambda intersect M equals to J, and this is for the outer union of the set gamma equals to rho intersect M equals to I. Notice that R of ij n plus 1 equals to the set rho such that Qi rho yield in one step star to Qj lambda. Thus, L of M equals to the union of the set of R of ij n plus 1 such that Qi in S intersect Qj in F. Since the union of a finite number of regular languages is again regular, theorem 6.16 will follow once we verify the lemma below. Lemma 6.17, for all ijk, R of ijk is regular. Proof of lemma 6.17. We prove lemma 6.17 by induction upon K, the hypothesis being that R of ijp is regular for all p which is less than equals to k. For k equals to 1, R of ij1 equals to the set rho such that delta of Qi rho equals to Qj. Then R of ij1 is finite and hence regular. Now we claim that R of ijk plus 1 equals to R of ijk union R of ikk followed by R of kkk star followed by R of kjk. To see that the claim holds, note that R of ijk plus 1 is the collection of strings rho with Qi rho moving to Qj lambda without using states with indices which is greater than equals to k plus 1. Now to go from state Qi to state Qj without involving Qm, for m which is greater than equals to k plus 1, we must choose one of the following options. A. Go from Qi to Qj and only involve states Qp for p which is less than k. This is the set R of ijk. B. Otherwise go from Qi to Qj and necessarily involve Qk. Therefore, we must choose one of the three sub-options below. 1. First, go from Qi to Qk using only Qp for p which is less than k. This is R of ikk. To go from Qk to Qk some number of times using only states Qp for p which is less than k. This is R kkk each time, and hence gives R of kkk star. 3. Finally, go from Qk to Qj only using states Qp for p which is less than k. This is R of kjk. Figure 6.6 may be helpful in visualizing option B above. Thus, the contribution of B is R of IKK followed by R of KKK star followed by R of KJK. Now we can apply the induction hypothesis to each of the expressions in the decompositions of R of IJK plus 1 of the claim. This observation establishes the claim, and hence the lemma and finishes the proof of theorem 6.16. Example 6.18. Figure 6.7 demonstrates the construction of a non-deterministic automaton accepting a given regular expression, let L equals to L of the star of AB union ABB. Example 6.19. Armed with the theorem 6.16, it is easy to write a language that takes exponential time for Thompson's construction, a deterministic automaton accepting the language L equals to the star of 0 union 1 followed by 0 followed by 0 union 1 n times can be shown to require big O of 2 to the n states, but is accepted by a non-deterministic automaton with big O of n states. Exercise 1. We remark that it is possible to construct a non-deterministic finite automaton with k plus 1 states, for which any deterministic automaton requires 2 to the k plus 2 states.